My name is Federico Zenith. I'm a senior research scientist at the SINTEF Research Institute in Trondheim, Norway. I'm the coordinator of the StasHH project for the development of a standard module for fuel cells in heavy-duty applications. My company, SINTEF, is responsible not just for coordination of the project, but also for the development of the digital interface of this standard and for the development of an X-in-the-loop software that has been demonstrated inside project. Initially, we were contacted by VDL, that is an industry partner, in 2019, when they were going to write the new call from Europe. And there was, in general, a very strong interest from the industry for a standard, because everybody was getting tired of reinventing the wheel every time they had a new deployment. And VDL was especially tired because they have several products, such as buses, trucks, gensets, and for every one of these, there were different products that did not fit each other. The project involves the development of a fuel cell standard for heavy-duty applications, but it's not just the development on paper. It involves also the construction of actual prototypes for many fuel cell module manufacturers, almost all of them in Europe, with participation also from other continents, though. The work also includes the testing of these modules, and the reason we have so much experimental activity is that previously some standard setting projects ended up only producing paper, and you this time wanted to make sure that, yes, you're going to produce paper, but you got to show that it is actually doable and that it is possible to build these modules, and these have to be built and offered by these companies. I think a significant challenge was that about half our consortium is composed of companies competing with each other. That is all the fuel cell manufacturers, and this project is actually about their bleeding edge of research. So usually data management is one of those boxes to check in a EU project. In this case, it was actually very important to make sure that the intellectual property stayed within each company and that each company felt comfortable continuing in this project. I think this worked out fine eventually, but it definitely required more attention than usual. Another challenge was the sheer size of the consortium. We have over 20 participants. Several of them, as mentioned, are competing with each other. And of course, they have to agree on a single standard, and that includes OEMs producing trucks, producing ships, producing smaller boats, producing buses, and so on. And eventually it turned out that the most important application is the European-sized trucks, not because we don't like America, but because American trucks are bigger. European trucks are smaller, have a smaller space, and their size is critical, and it ended up to be the most important dimension to determine the actual size of our standard modules. The open standard developed by StasHH is divided in three main parts. One is the size, which is arguably the most important, and that's because once you develop a bus or a truck, you have a certain chassis and you have very limited margin to change it. So it's important that the next generation of fuel cells fits in the same slot. Otherwise, it's a showstopper. The second part is the interfaces. You want to know where the hydrogen goes, where the air goes, where the cooling goes, and so on. And that is also quite important since you cannot simply move rigid pipes around this box. And then the final one is the digital interface, or the communications interface, where you, in a standard way, can tell the fuel cell module to start, to stop, to produce so much power. This standard is open for anyone to read and develop, and we hope it will be adopted by the community. The standard is already been adopted by several actors, and not just those directly in the project. The idea is to ensure that all fuel cell manufacturers in the project, and possibly others, start offering such modules in their product lineup, and so that user can start exploiting this standard. What is particularly important is the adoption of the standard by smaller actors. Big companies like several of those in our project have the resources to develop their own fuel cells, like, for example, Toyota does. They have the resources to build specific prototypes, but in my experience, I found a lot of mid-sized companies that are a bit skeptical about deploying fuel cell solutions because they can't really afford hiring a team of 10 engineers just for fuel cells. And they end up saying, okay, we just stick with the old technology until the new one is unavailable. Once you know where fuel cells fit and what is their interface, it's a lot easier to deploy them. Well, obviously, the role of CSP is extremely important, not just for the funding itself, because the fuel cell module suppliers actually operated on a very limited funding, about 50% on average, I believe. The greatest contribution was the networking, because this is a kind of project you can only do on a European scale or a continental scale if we were in America. But we actually involved companies from Japan, South Korea, North America, and not just European ones. So we needed this kind of networking effect in order to deploy a standard that can be considered global and can actually have an impact worldwide. I think what we stand to gain from this project is a much quicker deployment of fuel cell technologies in the heavy-duty sector. The heavy-duty sector, compared to the private car sector, is much more fragmented. And while when you make a hydrogen car, you expect to make a lot of these cars and can make an integrated solution within your own company, the number of heavy-duty vehicles for every model is much smaller. So having a standard for how to introduce fuel cells in these many niches is very impactful and very important.